Welcome to Sleep Knowledge. It's lovely to have you here. Before we begin, I'd love to know, where in the world are you watching from tonight? A quiet bedroom, a sleepy train ride, a cozy couch with a warm cup of tea. Wherever you are, I hope you're comfortable, safe, and ready to gently drift into thought. If you enjoy these relaxing explorations and would like to hear more, a like and subscribe really helps this sleepy little channel float along. And to those of you already subscribed, thank you. Truly, your support means more than you know. Now, I'll try not to make tonight's topic so interesting that it keeps you wide awake, but if it does, at least you'll have a better understanding of why particles sometimes act like waves and why reality seems to hesitate until someone's watching. A small price to pay for a restless night. So, let's begin, shall we? Have you ever wondered what the world looks like when you peel back every layer? When you look past what your eyes can see, past what your hands can touch? The everyday world feels so dependable. Objects stay where you put them. When you turn on a light, photons stream out in predictable ways. Drop something, and gravity pulls it down without fail. For centuries, this predictability felt complete. Scientists in the 1800s had built elegant mathematical descriptions of motion, heat, electricity, and light. Everything seemed to fit together like pieces of a grand puzzle, and many believed the puzzle was nearly finished. Just a few small details left to sort out. But then something unexpected happened. When researchers started examining the behavior of extremely tiny things far smaller than anything visible to the eye, atoms and the light they emit, the old rules stopped working. Not because the measurements were wrong, not because the equipment was flawed, but because reality itself, at its smallest scales, operates by a completely different set of principles. This is the world of quantum physics, a place where particles can be in two locations simultaneously, where observing something changes its behavior in ways that have nothing to do with disturbing it physically, where empty space hums with invisible energy, and where the future isn't written until the very moment it becomes the present. Tonight, we'll explore this strange realm together, gently and without rushing. You don't need to memorize anything or solve any equations. Just let the ideas wash over you like a calm tide. We'll wander from discovery to discovery, meeting the questions that puzzled scientists a century ago and still puzzle them today. So close your eyes if you'd like, adjust your pillow, let your breathing slow, and let's step into a universe where certainty gives way to possibility, and where even the word real starts to mean something beautifully different. There's a certain comfort in the way the world worked before quantum physics. Back in the late 1800s, scientists felt they had nearly everything figured out. Newton's laws explained how objects moved. Thermodynamics described heat and energy. Maxwell's equations captured the behavior of electricity and magnetism, including light itself. It was a time of confidence. Some physicists even suggested there wasn't much left to discover, only minor details to clean up and measure more precisely. The universe seemed like a well-oiled machine, predictable and knowable down to the smallest gear. But nature had other plans. One of those small details that seemed trivial at first turned out to unlock an entirely new way of understanding reality. It involves something wonderfully ordinary. What happens when you heat an object until it glows? Think of a piece of iron in a blacksmith's forge. As it heats, it begins to glow. First a dull red, then orange, then brilliant yellow-white if you get it hot enough. This glow is called thermal radiation, and every object that has temperature emits it. The hotter something gets, the more energetic the light it produces, shifting from red toward blue as temperature increases. This seems straightforward enough to explain using the physics of the time. Light is a wave, after all. Heat an object, and it should emit waves of electromagnetic radiation. Scientists could write down equations describing this process, and they expected those equations to match what they observed in laboratories. But here's where things got strange. When physicists actually calculated what the equations predicted, the results were absurd. According to their math, a hot object should emit infinite amounts of energy at very short wavelengths, particularly in the ultraviolet range and beyond. Obviously, this doesn't happen. A hot poker doesn't bathe you in infinite ultraviolet radiation. Something was deeply wrong with the theory. This impossible prediction became known as the ultraviolet catastrophe. It sounds dramatic, and it was. The math that worked so beautifully for large-scale physics was producing complete nonsense when applied to light and heat at small scales. A German physicist named Max Planck found himself staring at this problem in the year 1900. Planck was methodical, careful, conservative in his thinking. He wasn't looking to overturn the foundations of physics. He just wanted the equations to match reality. And in trying to fix them, he stumbled onto something revolutionary. What if, Planck wondered, energy doesn't flow smoothly and continuously? What if instead it comes in tiny, discrete chunks, like individual drops of water instead of a continuous stream? He called these chunks quanta, meaning fixed amounts. Each quantum of energy would be incredibly small, but real nonetheless. This was a strange idea. Nothing in classical physics suggested energy should be chunky. But when Planck added this assumption to his mathematics, something remarkable happened. The infinite energy problem disappeared. The equations suddenly matched what experimenters observed in their laboratories. Hot objects radiated exactly as much energy as they should, across all wavelengths, with no catastrophe in sight. Planck introduced a number, now called Planck's constant, to describe the size of these energy packets. It's astonishingly tiny, so small that in everyday life we never notice that energy is quantized. To us, it feels continuous, like water from a tap feels continuous, even though it's made of individual molecules. Even Planck himself didn't quite believe his own solution was real. He thought it was probably just a mathematical convenience, a trick to make the numbers work. Surely someone would come along later with a more sensible explanation that didn't require energy to come in packets, but that's not what happened. Planck had opened a door, and through that door lay an entirely new understanding of reality. His quanta weren't just a mathematical tool. They were real. They pointed to something fundamental about how nature operates at the smallest scales. Energy, it turns out, truly does come in discrete units. You can have one quantum or two quanta, but not 1.5. It's quantized, like counting apples or pennies. This discovery marked the beginning of quantum theory. It was tucked into a paper in 1900, presented without fanfare or grand claims, just a quiet solution to a frustrating problem. But that small constant, that peculiar idea about energy packets, would grow into one of the most successful and mind-bending theories in all of science. From that moment forward, physics would never feel quite finished again. There would always be deeper mysteries waiting, stranger truths to uncover. Now, you might think that after Planck's discovery, physicists would have immediately realized the world was quantum. But science rarely works that way. Most researchers treated Planck's quanta as a useful mathematical device, nothing more. Light was still understood as a wave, smooth and continuous, spreading through space like ripples on a pond. That understanding was about to change, thanks to a puzzle involving light and metal and a young physicist named Albert Einstein. The puzzle was called the photoelectric effect. Here's how it works. When you shine light onto certain metals, electrons pop out of the surface. This wasn't particularly mysterious in itself. Light carries energy, so it made sense that hitting metal with light could shake some electrons loose. But the details didn't make sense at all. According to the wave theory of light, brightness should determine how much energy is delivered to the electrons. Shine a brighter light, and the electrons should come flying out with more energy. Shine a dimmer light and they should dribble out more slowly with less energy. That's not what happened. Researchers found something baffling. Brightness didn't control the energy of the ejected electrons. Frequency did. Low-frequency light, even if incredibly bright, wouldn't eject any electrons at all. But high-frequency light, even if dim, would send electrons flying with considerable energy. It was as though each electron needed a certain minimum push to escape the metal, and that push had to come all at once. More light didn't help unless each individual bit of light packed enough punch. In 1905, Einstein proposed a beautifully simple explanation. What if light wasn't truly a continuous wave? What if it was actually made of particles? Tiny packets of energy traveling through space. He built on Planck's idea, suggesting that light came in quanta, which we now call photons. Each photon carries a specific amount of energy, determined by the light's frequency. High-frequency light means high-energy photons. Low-frequency light means low-energy photons. When a photon strikes an electron in the metal, it delivers all its energy at once, in one lump sum. If that energy is enough, the electron escapes. If not, nothing happens. This explained the photoelectric effect perfectly. Brightness is just how many photons you have. Frequency determines how much energy each one carries. A million low-energy photons still won't free an electron if none of them individually has enough energy. But a single high-energy photon can do the job easily. Einstein's idea was radical. Light is particles, but light creates interference patterns, diffracts around corners, does all the things waves do. How could it be made of particles? Einstein didn't deny light's wave nature. Instead, he suggested something even stranger. Light is both. It's a wave and a particle, depending on how you look at it and what you're measuring. This wave-particle duality became one of the central mysteries of quantum physics. Imagine sunlight streaming through your window. If you look at how it spreads and bends, it behaves like a wave. But if you could see individual interactions, photons striking atoms in your retina, you'd find discrete particles, each carrying a specific quantum of energy. Both descriptions are true, both are real. Reality at this scale doesn't fit into our everyday categories. For this explanation of the photoelectric effect, Einstein received the Nobel Prize in 1921. Interestingly, not for his theory of relativity, which is what most people remember him for, but for this quantum insight about the nature of light. What makes this even more fascinating is that Einstein himself became deeply uncomfortable with where quantum physics was heading. As the theory developed through the 1,920 seconds, it became increasingly probabilistic, increasingly strange. Einstein famously resisted this direction. God does not play dice with the universe, he wrote, expressing his belief that underneath all the quantum strangeness, there must be a deeper, deterministic reality. But the evidence kept pointing the other way. Light really does behave as both wave and particle. Energy really does come in chunks. And as we'll see, the strangeness was only beginning. The quantum world had revealed one of its core truths. At the smallest scales, nature doesn't respect our tidy categories. Things can be both this and that, here and there, wave and particle, all at once. It's not that our understanding is incomplete, it's that reality itself is fundamentally different than our everyday experience suggests. And this leads to one of the most famous experiments in all of physics. An experiment so simple a child could do it, yet so profound it still puzzles scientists today. Let's talk about two slits, a screen, and the mystery of observation itself. Picture this. You have a light source, a barrier with two narrow slits cut into it, and a screen on the other side to catch whatever makes it through. When you shine light through both slits, what pattern appears on the screen? If light were simply particles, like tiny marbles, you'd expect two bright strips on the screen, one behind each slit. That's how particles should behave. They go through one slit or the other and pile up on the other side in two distinct groups. But that's not what happens. Instead, you see multiple bright and dark bands, an interference pattern. This is exactly what waves do. When waves pass through two openings, they spread out and overlap on the other side. Where two wave peaks meet, they reinforce each other, creating bright bands. Where a peak meets a trough, they cancel out, creating dark bands. So light is acting like a wave. No surprise there, at least not in the 1800s when this experiment was first performed. Light is a wave, everyone agreed. The interference pattern proves it. But now comes the quantum twist. What if you turn down the light so dim that only one photon is traveling through the apparatus at a time? Surely now we'll see particle behavior, right? Each photon will go through one slit or the other, and gradually, as thousands of photons accumulate on the screen, we'll see two bright strips. Except that's not what happens. Even sending one photon at a time, the interference pattern builds up. Each photon lands at a single point, like a particle. But over time, those points form the same wave-like interference pattern. Dark bands where photons never land, bright bands where they concentrate. How is this possible? How can a single photon interfere with itself? It's as though each photon somehow goes through both slits simultaneously, interferes with itself like a wave, then lands at a single point like a particle. The photon acts as a wave of possibilities, exploring all available paths until it's detected, at which point it becomes a definite event at a specific location. But the strangeness deepens. What if you place detectors at the slits to see which one each photon actually goes through? Surely we can just watch and find out. The moment you do this, the interference pattern vanishes. As soon as you measure which slit the photon passes through, it stops behaving like a wave spreading through both slits. It becomes a particle going through one slit or the other. Now you get two bright strips on the screen, exactly like you'd expect from particles. Simply observing, simply checking which path the photon takes, changes the outcome. Turn the detectors off, and the interference returns. Turn them on, and it disappears. It's not that your detectors are physically bumping the photons and disturbing them. Even gentle, passive observation has this effect. It's as though the photon somehow knows whether you're watching, or more accurately, whether information exists about which path it took. If that information exists, even if you don't look at it, the photon behaves like a particle. If that information doesn't exist, the photon behaves like a wave. This isn't a quirk of photons. Researchers have done this experiment with electrons, with whole atoms, even with large molecules containing hundreds of atoms. The results are always the same. Unobserved, they behave like waves, creating interference patterns. Observed, they behave like particles, creating discrete impacts. What does this tell us? The act of measurement, the act of knowing, seems to play a fundamental role in determining what happens. Not because we're clumsily disturbing things with our instruments, but because the quantum world genuinely exists in a state of possibility until a measurement forces it to become definite. Before measurement, the photon doesn't have a specific path. It's not secretly going through the left slit or the right slit while we're not looking. It exists in what's called a superposition, a state of being in both places at once, exploring both possibilities. Only when we measure does it collapse into having taken one definite path. This is one of the deepest mysteries in quantum physics. What is observation? Why does it matter? Does it require a conscious mind, or does any interaction with the environment count? These questions don't have universally agreed upon answers even today, more than a century after the first quantum experiments. But what's clear is this: at the quantum scale, reality is not a fixed thing waiting to be discovered. It's a shimmering cloud of possibilities that crystallizes into definite outcomes only when observed. The universe, in a very real sense, is participatory. We're not just passive observers looking at an objective reality. We're part of the process by which reality takes shape. Think about that as you drift towards sleep tonight. The act of seeing, of knowing, of measuring plays a role in what exists. Observation isn't just about gathering information. It's about bringing possibilities into being, collapsing the hazy and uncertain into the sharp and definite. And this leads us to one of the most important equations ever written. An equation that doesn't just describe particles in motion, but describes clouds of possibility flowing through time. In the mid-1920s, an Austrian physicist named Erwin Schrödinger was trying to make sense of the bizarre behavior of quantum particles. Physicists knew that particles could act like waves, but they needed a mathematical framework to describe those waves and predict how they'd evolve. Schrödinger developed an equation that does exactly that. It's called, appropriately enough, the Schrödinger equation, and it's the beating heart of quantum mechanics. Don't worry, we won't write it out or solve it, but understanding what it represents can give you a beautiful insight into how the quantum world works. The key concept is something called the wave function. Think of it as a mathematical description of all the possible states a quantum system could be in. Where might an electron be? The wave function tells you, not with certainty, but with probabilities. It describes a cloud of likelihood spreading through space. When you solve Schrödinger's equation, you're essentially watching this cloud evolve over time. The equation tells you how the wave function changes from one moment to the next, how it spreads, contracts, interferes with itself, and flows around obstacles. Here's what makes it so remarkable. The wave function doesn't describe a particle's actual position. It describes the probability of finding the particle at various locations if you were to measure it. Before measurement, the particle doesn't have a definite position. It exists as this spread out wave of potential locations. Only when you measure does the wave function collapse. Suddenly, all those possibilities condense into one actual outcome. You find the electron here, not there. The wave function, which was spread out over a large region, instantly becomes concentrated at a single point. This is strange, perhaps even unsettling. It means that before measurement, an electron doesn't really have a position in the way we usually think about it. It's not that we don't know where it is. It's that where is not yet a meaningful concept. The electron is nowhere in particular and everywhere possible, all at once. Schrödinger's equation has been extraordinarily successful. It correctly predicts the behavior of atoms, the structure of molecules, the way electrons arrange themselves around atomic nuclei. It explains why atoms are stable, why they emit light at specific colors, why chemical bonds form. One of its early triumphs was explaining the hydrogen atom. Before quantum mechanics, nobody could figure out why the electron orbiting a hydrogen nucleus didn't spiral inward and crash. Classical physics said it should radiate energy and collapse. Schrödinger's equation revealed that electrons don't orbit like planets around the sun. Instead, they form standing wave patterns around the nucleus. These patterns are stable. The electron is like a vibration on a drumhead, resonating at certain allowed frequencies. Change the frequency, and you change the energy level. But in between those allowed levels, stable states don't exist. These allowed patterns are what we call electron orbitals. You might have seen pictures of them, strange shapes like spheres, dumbbells, and more complex forms. Those aren't paths the electron follows. There are probability clouds, regions where the electron is likely to be found. Even Schrödinger himself struggled with the implications of his equation. He developed the math, but he wasn't entirely comfortable with the idea that particles don't have definite properties until measured. He later devised a famous thought experiment to highlight how absurd this seemed when applied to everyday objects. Imagine, he suggested, a cat in a closed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers the poison, and the cat dies. If it doesn't decay, the cat lives. According to quantum mechanics, until you open the box and observe, the atom exists in a superposition of decayed and not decayed, which means the whole system, including the cat, should be in a superposition of alive and dead. Schrödinger meant this as a critique, pointing out how absurd it seems to apply quantum rules to large objects. But the thought experiment became famous for capturing the central mystery. When does the quantum world of probabilities become the classical world of definite outcomes? Where's the boundary? Does the cat really exist in both states until someone opens the box? These questions still don't have universally accepted answers. But Schrödinger's equation remains the foundation of quantum mechanics, describing with beautiful precision how possibilities flow through time, how they interfere and combine, and how they eventually collapse into the single reality we observe. As you lie there, drifting between waking and sleep, you're in a kind of superposition yourself. Not quite awake, not quite asleep, existing in a hazy in-between state until the moment you fully transition to one or the other. The quantum world is strange, yes, but perhaps not entirely foreign to our experience after all. Now, there's another principle at the heart of quantum mechanics, one that tells us there are fundamental limits to what we can know. It's called the uncertainty principle, and it might be the most misunderstood idea in all of physics. In everyday life, we assume we can know everything about an object if we measure carefully enough. Where is it? How fast is it moving? With good enough instruments, you could measure both to arbitrary precision, but the quantum world doesn't allow this. In 1927, Werner Heisenberg discovered that certain pairs of properties can't both be known precisely at the same time. The more accurately you know one, the less accurately you can know the other. The most famous example involves position and momentum. Momentum is just mass times velocity, a measure of how much oomph something has in its motion. Heisenberg showed that there's a fundamental trade-off. If you pin down exactly where a particle is, its momentum becomes completely uncertain. If you measure its momentum precisely, its position becomes fuzzy. This isn't about our measuring tools being crude. It's not that better technology could fix it. The uncertainty is built into reality itself. It's a feature of nature, not a bug in our instruments. Why does this happen? It comes back to wave-particle duality. Remember, quantum particles are described by wave functions. A wave that's tightly localized, concentrated in a small region, has to be made up of many different wavelengths mixed together. Those different wavelengths correspond to different momenta, so localizing the position means uncertainty and momentum. Conversely, a wave with a very precise wavelength, meaning precise momentum, has to be spread out over a large region of space. You can't have both at once. Think of it like trying to hold mist in your hands. Squeeze tight to pin down where it is, and it disperses, slipping away. Cup your hands gently, letting it spread out, and you can hold more of it, but you've lost track of exactly where it is. This uncertainty has profound consequences. For one thing, it's why atoms are stable. You might wonder why the electron in a hydrogen atom doesn't just fall into the nucleus, attracted by the opposite charge. The uncertainty principle won't allow it. If the electron were sitting right on top of the nucleus, its position would be very well defined. That means its momentum would be highly uncertain. High uncertainty in momentum means the electron could have huge amounts of kinetic energy, far more than the electrical attraction provides. It would immediately fly away. The electron settles into a balance, a stable orbital where the uncertainties in position and momentum are minimized, but not zero. It can't collapse into the nucleus, and it can't fly away. It's locked into a quantum state, hovering at a certain average distance, neither here nor there exactly, but spread out in a probability cloud. The uncertainty principle appears in other pairs of properties too. Energy and time have a similar relationship. If you measure energy very precisely, the time becomes uncertain. This has a strange consequence. For a very brief moment, energy can fluctuate wildly, even seemingly coming from nothing, as long as it disappears quickly enough. This is why even empty space isn't truly empty, as we'll explore in a moment. But first, let's sit with the idea of uncertainty itself. It's telling us something beautiful and slightly melancholy about the nature of knowledge. We live in a universe where knowing has limits. Not because we're ignorant, not because our tools are inadequate, but because reality itself is built with a certain softness, a certain blur. You can't have perfect knowledge. The universe won't allow it. Some people find this disturbing, but there's another way to look at it. Uncertainty gives the universe room to breathe. It allows for spontaneity, for novelty, for things to happen that aren't strictly determined by what came before. Without uncertainty, reality might be too rigid to support the richness and complexity we see around us. As you rest there, not knowing exactly what thought will drift through your mind next, not knowing precisely when you'll fall asleep, you're experiencing a kind of uncertainty too, and that's okay. It's natural. It's how things are meant to be. In the quantum world, precision and certainty aren't always virtues. Sometimes the most accurate description of reality is one that embraces the haze, the blur, the maybe. Now, let's talk about something truly strange: superposition. We've touched on it already, but it's worth exploring more deeply because it's one of the most counterintuitive aspects of quantum physics. In your everyday experience, things are in definite states. A light is on or off. A door is open or closed. A coin shows heads or tails. Even before you look, you know it's one or the other. You just don't know which. Quantum systems don't work that way. Before measurement, they can genuinely exist in multiple states simultaneously. Not one or the other, but both. This is superposition. Take an electron spin. This is a quantum property that's sort of like the electron spinning on its axis, though that's not exactly what's happening. The spin can be up or down, but before you measure it, the electron isn't secretly spin up or secretly spin down. It's actually in a state of being both at once, a superposition of up and down. Only when you measure does it become one or the other. And here's the truly weird part. It's not that measurement reveals which state it was in all along. Measurement creates the definite state. Before you measured, both states were equally real, existing simultaneously. This isn't just theoretical. Superposition is the foundation of quantum computing. A classical computer bit is either 0 or 1. A quantum bit, or qubit, can be in a superposition of both 0 and 1 at the same time. This allows quantum computers to process multiple possibilities simultaneously, giving them potential advantages for certain types of calculations. But superposition is fragile. The slightest interaction with the environment can destroy it, causing what's called decoherence. The quantum system gets entangled with air molecules, stray photons, vibrations, anything around it. Once that happens, the superposition collapses. and the system behaves classically, settling into one definite state. This is why you don't see superposition in everyday life. Large objects are constantly interacting with their environment, constantly being measured in tiny ways by the world around them. Decoherence happens so fast that the object never gets a chance to exhibit quantum behavior. But at small scales, in carefully isolated systems, superposition is real and measurable. Particles genuinely exist in multiple states at once, and we can observe the consequences. This raises deep questions. If a particle can be in two states at once, what does that say about reality? Is the superposition physically real, or is it just a mathematical description of our knowledge? Different interpretations of quantum mechanics give different answers, but regardless of interpretation, the predictions are the same. Superposition is part of how the quantum world works, whether we fully understand it or not. As you hover on the edge of sleep, you might think of yourself as being in a kind of mental superposition. Part of your mind is still engaged with these ideas, still listening. Part has already drifted away into the beginnings of dreams. You exist in both states at once, until the moment you fully commit to one or the other. The quantum world teaches us that reality is richer, stranger, and more fluid than we ever imagined. Things can be multiple ways at once. The universe doesn't always insist on definite answers until we ask definite questions. And now we come to one of the spookiest phenomena in all of quantum physics: entanglement. Imagine two particles that interact in a certain way, becoming linked. Once they're entangled, measuring one instantly affects the other, no matter how far apart they are. It's as though they remain connected by an invisible thread, sharing a quantum state even across vast distances. Let's say you have two entangled photons. Each can be polarized vertically or horizontally. Before measurement, neither has a definite polarization. They're both in superposition, but they're linked in such a way that if you measure one and find it vertically polarized, the other will instantly be horizontally polarized, even if it's on the other side of the galaxy. This isn't because they secretly decided ahead of time which would be which. Until you measure, neither has a definite state. But the moment you measure one, both states become determined instantly. Einstein called this spooky action at a distance, and he didn't like it. He thought it meant quantum mechanics was incomplete, that there must be hidden information determining the outcomes all along. In the 1,960 seconds, physicist John Bell devised a way to test this, and the experiments came down firmly on the side of quantum mechanics. Entanglement is real. This doesn't mean you can send information faster than light. The outcomes are random. You can't control what result you get when you measure your particle, so you can't use it to send a message. But the correlation is real. The particles are genuinely connected in a way that transcends space. Entanglement is being used in developing technologies. Quantum cryptography uses entangled particles to create unbreakable codes. If someone tries to intercept the signal, they disturb the entanglement, and the intrusion is immediately obvious. Quantum computers rely heavily on entanglement. It's part of what allows them to process information in ways classical computers cannot. But perhaps the deepest implication of entanglement is philosophical. It suggests that the universe is fundamentally interconnected. Particles that have interacted carry a kind of memory of that interaction, remaining linked no matter how far they separate. Separation, at the quantum level, is partly an illusion. Things that seem distant and independent may still be profoundly connected beneath the surface. The universe is woven together in ways we're only beginning to understand. As you rest, your mind and body seem separate from the world around you, but at the deepest level, you're made of atoms that have interacted with countless other atoms. You're part of an immense, interconnected web, entangled with the universe in ways too subtle to perceive, but real nonetheless. Now let's explore something that sounds impossible: tunneling. In the classical world, if you don't have enough energy to get over a barrier, you can't cross it, throw a ball at a wall, and if it's not moving fast enough, it bounces back. It doesn't magically appear on the other side. But in the quantum world, particles can do exactly that. It's called quantum tunneling. A particle can pass through a barrier even if it doesn't have enough energy to climb over it. This happens because of the wave nature of particles. The wave function doesn't stop abruptly at a barrier. It fades, but it extends slightly into and even through the barrier. If the barrier is thin enough, there's a small but non-zero probability that the particle will be found on the other side. It doesn't climb over. It doesn't smash through. It simply appears on the other side, as though it tunneled through a region it shouldn't be able to enter. Tunneling is essential to many processes. Radioactive decay happens partly through tunneling. Particles inside an atomic nucleus are trapped by a powerful force. Classically, they shouldn't be able to escape, but quantum tunneling allows them to occasionally pop through the barrier and escape. The sun shines because of quantum tunneling. In the sun's core, hydrogen nuclei need to fuse together, but they're positively charged and repel each other. Even with the intense heat and pressure in the sun's core, they don't quite have enough energy to overcome that repulsion classically. But quantum tunneling allows them to get close enough, often enough, for a fusion to occur. Without tunneling, the sun wouldn't shine, stars wouldn't burn, the universe would be a much darker, colder place. Tunneling is used in technology too. Scanning tunneling microscopes can image individual atoms by measuring the tunneling current between a sharp tip and a surface. The amount of tunneling is exquisitely sensitive to distance, allowing researchers to map out atomic structures with incredible precision. As our electronic devices get smaller and smaller, approaching atomic scales, quantum tunneling becomes a problem. Electrons can tunnel through barriers that are supposed to insulate different parts of a circuit. Engineers have to design around this, or in some cases, embrace it and use tunneling intentionally. The phenomenon reminds us that barriers at the quantum level are not absolute. Walls are not truly solid. Particles explore possibilities beyond the obvious, sometimes finding paths that shouldn't exist. As you drift towards sleep, perhaps you're tunneling through a barrier yourself, passing from waking consciousness to dreams, through a transition that seems impossible to pin down exactly. One moment you're here, the next you're somewhere else entirely, and the crossing itself is hazy and uncertain. Quantum physics tells us that the impossible is sometimes just improbable. And given enough attempts, the improbable eventually happens. Speaking of the impossible, let's talk about empty space. You'd think empty space would be, well, empty, nothing there, a perfect void. But the quantum world says otherwise. Even when you remove every particle, every bit of matter and energy, space isn't truly empty. It's seized with quantum activity, with fluctuations and virtual particles popping in and out of existence. This comes from the uncertainty principle. Remember, energy and time are linked by uncertainty. For a very brief moment, energy can fluctuate wildly. Particle-antiparticle pairs can spontaneously appear, exist for a fleeting instant, then annihilate back into nothingness. These are called virtual particles. They're not directly observable, but they have real, measurable effects. One of the most striking is the Casimir effect. Place two metal plates very close together in a vacuum. The space between them restricts which virtual particles can exist there. Outside the plates, there's no such restriction. This creates a tiny imbalance in the quantum vacuum pressure. The plates are pushed together by a force that comes from, essentially, nothing, from the energy of empty space itself. This has been measured. It's real. The vacuum isn't empty, it's alive with fleeting quantum activity, a bubbling sea of potential energy. This vacuum energy may play a role in cosmology. There's a mysterious force called dark energy that's causing the universe's expansion to accelerate. Some physicists think it might be related to the energy of the quantum vacuum, though the details don't quite work out yet. It remains one of the biggest unsolved problems in physics. But the broader point is clear. At the quantum level, nothingness doesn't exist. Even the emptiest space is full of possibility, full of activity too brief and subtle for us to see directly, but real nonetheless, shaping the universe in quiet ways. As you lie in the darkness, in the quiet, remember that silence is never truly silent. Even in the stillness, countless processes are occurring, molecules vibrating, neurons firing, and at the deepest level, quantum fields humming with invisible energy. Rest is not the absence of activity. It's a different kind of activity, gentler and hidden. Now, all of this strangeness leads to a profound question. What happens when we observe a quantum system? We've talked about measurement collapsing the wave function, but we haven't really explained what causes the collapse. This is called the measurement problem, and it's one of the deepest puzzles in quantum mechanics. The Schrödinger equation describes how quantum systems evolve smoothly and deterministically, but when a measurement occurs, that smooth evolution suddenly stops. The wave function collapses, superpositions vanish, probabilities become certainties. What triggers this? Is it the presence of a conscious observer? Is it just any interaction with a large classical system? Is it something else entirely? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation, developed by Niels Bohr and others, essentially says the wave function is a tool for making predictions. Collapse happens when we gain information. Before that, asking what's really going on isn't meaningful. This is pragmatic but philosophically unsatisfying. The many worlds interpretation says the wave function never collapses. Instead, every possible outcome happens, but in different branches of reality. When you measure an electron's spin, the universe splits. In one branch, you see spin up, in another, spin down. Both are real. You just find yourself in one particular branch. This avoids the collapse problem, but at the cost of infinite parallel universes. Other interpretations suggest objective collapse mechanisms, where the wave function spontaneously collapses under certain conditions, perhaps related to gravity or the size of the system. The honest answer is, we don't know for sure. Quantum mechanics makes incredibly accurate predictions, but what it means, what's really happening when we measure, remains mysterious. Perhaps that's okay. Perhaps some mysteries are meant to stay mysterious, at least for now. The quantum world has taught us that reality is deeper and stranger than we can easily comprehend. We can describe it mathematically, we can use it technologically, but understanding it fully in a way that feels intuitive and obvious may be beyond our current reach. As you drift closer to sleep, your conscious mind loosening its grip on the world, you're experiencing your own collapse of sorts. The many possibilities of what you might think or dream narrow down to what you actually experience. But how that happens, why this thought and not that one, remains mysterious too. Consciousness and quantum mechanics may be more connected than we realize, or they may be entirely separate mysteries. Either way, both remind us that knowing has its limits. Let's end our journey tonight with a reflection. Quantum physics began as an attempt to solve small puzzles in how light and matter behave. It grew into a complete revolution in how we understand reality. The quantum world shows us a universe that's participatory, where observers and observed are intertwined, It's a universe built on probability, not certainty, where definite outcomes emerge from clouds of possibility. It's a universe where empty space hums with energy, where particles can be waves, where observation matters, where things separated by vast distances remain mysteriously connected. This isn't just abstract physics, it's reshaped technology. Lasers, semiconductors, computers, MRI machines, all of modern electronics relies on quantum mechanics. The device you're using right now, whatever it is, works because engineers understand how electrons behave in quantum ways. But beyond the practical applications, quantum physics has changed how we think about existence itself. It's made reality softer, stranger, more open to interpretation. It's shown us that the universe doesn't insist on being comprehensible in everyday terms. It plays by its own rules, rules that feel alien to creatures evolved to navigate a classical world of medium-sized objects moving at moderate speeds. And yet, there's a poetry to it, a beauty in the uncertainty, in the way possibilities shimmer before collapsing into actuality. A grace in how the universe holds multiple truths at once, resolving them only when asked. As you lie there, you're made of quantum particles, your atoms, your molecules, the very electrons carrying signals through your nervous system, all of them dancing to quantum rules. You are, in a very real sense, a quantum system, though one so large and so entangled with your environment that you behave classically. But at the deepest level, you're part of this strange quantum tapestry. You're a pattern in fields that fill all space. You're a collection of probabilities that have collapsed into one particular arrangement, one particular person, lying here, listening, drifting, and that's miraculous. Out of all the possible ways quantum fields could arrange themselves, they've arranged themselves into you. Into consciousness, thought, experience, into someone capable of wondering about the nature of reality itself. Quantum physics doesn't have all the answers. It raises as many questions as it solves, but it points towards something profound, that the universe is not a dead mechanism. It's alive with possibility. It's creative, surprising, endlessly subtle. Reality, at its heart, is not solid and fixed. It's a dance of probabilities, a web of connections, a process of becoming. And you're part of that process. You're not separate from the quantum world. You're woven into it, participating in the great unfolding. So rest now. Let your thoughts slow and scatter. Let the definite give way to the hazy and uncertain. Let yourself drift into that strange space between waking and sleep, where possibilities hover and multiply before collapsing into dreams. The quantum world will still be here in the morning, strange and beautiful as ever, quietly humming beneath everything you see and touch. And maybe, just maybe, understanding that will make the everyday world feel a little more magical, a little more full of wonder. Now, as we continue deeper into the quantum realm, there's something truly remarkable we haven't fully explored yet. It's the way quantum mechanics shapes the very atoms that make up everything around you, including your own body. You see, before quantum physics, atoms were a complete mystery. Scientists knew they existed. They'd measured their effects, weighed them indirectly, understood that matter was made of these tiny building blocks, but nobody could explain why atoms were stable or why they behaved the way they did. Classical physics said atoms shouldn't exist at all. If electrons orbit the nucleus like planets around a sun, they should be constantly radiating energy, spiraling inward in a fraction of a second. Every atom should collapse. Matter itself shouldn't be stable. But matter is stable. You're stable. The pillow beneath your head, the air you breathe, all of it persists, moment after moment, held together by quantum rules that don't exist in the classical world. When physicists applied quantum mechanics to atoms, Everything suddenly made sense. Electrons don't orbit. They exist in quantum states, probability clouds surrounding the nucleus. These states are stable because of wave properties. An electron in an atom is like a standing wave, a vibration that fits perfectly around the nucleus without changing over time. Only certain standing waves are possible, just like only certain notes can resonate in a musical instrument. These allowed states are what we call energy levels. An electron can be in the ground state, the lowest energy level, or in excited states with more energy. But it can't be in between. It has to jump from one level to another, releasing or absorbing a quantum of energy, a photon, when it does. This is why atoms emit light at specific colors. Each jump between energy levels corresponds to a photon of a particular energy, which we perceive as a specific color. Hydrogen glows with its characteristic reddish-pink hue because its electrons make specific quantum jumps, emitting photons of specific wavelengths. Every element has its own unique pattern of energy levels, its own quantum fingerprint. This is how we can identify elements in distant stars just by looking at the light they emit. The quantum jumps of electrons billions of light years away follow the same rules as electrons here on Earth. As you rest there, the atoms in your body are all in their various quantum states, stable and unchanging for now, held together by rules that seemed impossible when first discovered but are now fundamental to our understanding of reality. And speaking of fundamental understanding, there's something beautifully strange about how we describe quantum particles. We've been talking about electrons as if they're individual things, but in quantum field theory, the deeper framework, even particles themselves are just ripples in underlying fields. Imagine space filled with invisible fields, one for electrons, one for photons, one for every type of particle. These fields permeate all of reality, existing everywhere at once. What we call a particle is just a localized vibration in its field, a ripple traveling through an ocean that fills the universe. When you create an electron, you're not really creating something from nothing. You're exciting the electron field, causing it to vibrate in a particular way. That vibration is what we detect as a particle. Destroy the electron, and the vibration fades, but the field remains, ready to be excited again elsewhere. This perspective makes certain things easier to understand. How can particles be created and destroyed? Easy. They're just vibrations that can start and stop. How can a particle be in multiple places at once? The underlying field exists everywhere, so its vibrations can spread out over large regions. Even more beautiful, this framework explains forces. Electromagnetic force comes from exchanges of photons, vibrations in the electromagnetic field passing between charged particles. The particles don't touch directly. They interact by sending ripples through the fields between them. You could think of it like people in a swimming pool, causing waves that push and pull on each other without ever touching. The field is the medium, and particles are the disturbances traveling through it. This vision of reality, fields vibrating in complex patterns, is both abstract and profound. You're not made of tiny solid balls called atoms. You're made of intricate vibrations in quantum fields, patterns of energy that have somehow organized themselves into something capable of reading these words, thinking these thoughts, feeling tired and ready for sleep. It's a perspective that makes you feel both smaller and more connected. Smaller because you're just a pattern, one particular arrangement among infinite possibilities. More connected because those same fields extend throughout the universe. You're made of the same fundamental stuff as stars, as galaxies, as everything that exists. There's something deeply soothing about that, isn't there? You're not separate from the cosmos. You're a part of it, woven from the same quantum fabric as everything else. But let's explore something that bridges our everyday experience with this quantum strangeness. The photoelectric effect that Einstein explained. It's not just historical curiosity. It's the principle behind solar panels that convert sunlight to electricity, powering homes and devices all around the world. When photons from the sun hit a solar cell, they kick electrons free from atoms in the material, just as Einstein described. Those freed electrons flow as electrical current. The quantum nature of light, the fact that it comes in discrete packets with specific energies, is essential to how this works. Different materials absorb different colors of light because their electrons need different amounts of energy to break free. Engineers design solar cells to match the spectrum of sunlight, choosing materials whose energy levels align with the photons the sun provides most abundantly. This is quantum mechanics in action, every day, on your rooftop or in solar farms spanning acres. Millions of photons streaming from the sun, each carrying its quantum of energy, each potentially freeing an electron, collectively generating the power that runs our world. And it's not just solar panels. Light-emitting diodes, LEDs, work on the opposite principle. Force electrons to jump down from a higher energy level to a lower one, and they emit photons. The color of the LED depends on the size of the energy gap, which depends on the quantum properties of the semiconductor material. The screen you might be watching this on, if it's an LED or OLED screen, is a quantum device. Every pixel is composed of quantum dots or semiconductor materials precisely engineered to emit specific colors when electrons make quantum jumps. The brightness of each pixel depends on how many electrons are jumping, how many photons are being created. You're surrounded by applied quantum mechanics. Your LED lights, your computer chips, your phone, your medical devices, all of them work because engineers understand and exploit quantum effects. The strange world of quanta isn't just abstract theory, it's the foundation of modern technology. And here's something that might help as you drift towards sleep. These quantum processes are probabilistic, but when you have trillions upon trillions of particles, the average behavior becomes extremely predictable. Each individual photon hitting a solar cell has some probability of freeing an electron. You can't predict which specific photon will succeed. But with billions of photons arriving every second, the overall current is steady and reliable. This is how quantum randomness gives rise to classical predictability. In large numbers, the statistics smooth out. The uncertainty at the micro level averages away, leaving dependable, consistent behavior at the macro level. You can relax into that predictability. Your bed will stay solid, your room will stay intact. Quantum fluctuations of individual particles don't create chaos in the everyday world. They average out, leaving stability and order. There's a beautiful irony in this. The quantum world is fundamentally uncertain, probabilistic, strange, and yet, from that uncertainty emerges the reliable, predictable, classical world we experience. Order from chaos, certainty from probability, the familiar from the bizarre. This is the miracle of large numbers, of statistical averaging, of emergent properties. The whole is different from the parts. The behavior of trillions of quantum particles gives rise to classical objects that follow entirely different rules. Rules we can understand and predict and rely upon. So even though you're made of quantum particles, even though uncertainty is woven into your fundamental nature, you can still trust in the stability of the world around you. The quantum strangeness averages out, leaving something solid, dependable, safe. As you rest there, you're both quantum and classical, both uncertain and stable, both particle and pattern. You're a bridge between two worlds, embodying both the strange and the familiar, both the microscopic and the macroscopic, and that's a good place to be, poised between two realms, partaking of both, limited by neither. You can appreciate the quantum mysteries while enjoying classical stability. You can wonder at the strangeness while resting in certainty. The quantum world gives you possibility. The classical world gives you structure. Together, they give you reality, rich and complex, mysterious and knowable, strange and familiar, all at once. Let that duality soothe you as you drift towards sleep. You don't have to choose between quantum and classical, between uncertainty and order. You can be both. You are both. And that's perfectly fine, perfectly natural, perfectly right. Good night, traveler between worlds. May your dreams be quantum, full of superposition and possibility. And may your sleep be classical, stable, and restorative. The universe holds space for both, as it holds space for you, exactly as you are. From Sleep Knowledge. Thank you for this journey. Rest well. Now let's talk about something called the Stern-Gerlach experiment, which revealed one of the most peculiar properties of quantum particles. When you send a beam of silver atoms through a magnetic field, the atoms split into two groups, deflecting either up or down, never in between. This showed that particles have an intrinsic property called spin, and it's quantized. An electron's spin is either up or down, never part way. This isn't the particle physically rotating. It's an intrinsic quantum property, a kind of built-in angular momentum that doesn't have a classical analog. Spin is fundamental to how matter behaves. The Pauli exclusion principle, which we touched on earlier, applies to particles with half-integer spin. Two electrons can occupy the same orbital only if their spins point in opposite directions. This spin pairing is why chemistry works, why atoms bond in the specific ways they do. Spin also makes possible technologies like magnetic resonance imaging, MRI. The nuclei of atoms in your body, particularly hydrogen nuclei, have spin. When placed in a strong magnetic field, these spins align either with or against the field. Radio waves can flip the spins, and when they flip back, they emit signals that can be detected. Different tissues in your body contain different amounts of hydrogen and different environments for those hydrogen nuclei. So the MRI signals vary from tissue to tissue, creating detailed images of your internal structures without any surgery or radiation. It's remarkable. Doctors can see inside your body, diagnose diseases, guide treatments, all because quantum particles have this intrinsic property called spin, and we've learned to detect and manipulate it. Your body is full of spinning quantum particles right now. Every nucleus, every electron, carrying its quantum spin, aligned randomly in the absence of strong fields, but each one a tiny magnetic moment, a little quantum compass pointing in some direction. You're a quantum ensemble, billions upon billions of tiny spins, mostly random, mostly canceling each other out, but collectively creating the bulk properties of matter, the magnetic susceptibilities, the interactions that make chemistry and biology possible. As you rest, all those spins continue their quantum existence, neither fully up nor fully down until measured, existing in superpositions, contributing to the quantum nature of your being. Let's think about quantum entanglement from another angle. We talked about particles being entangled, but there's something called entanglement entropy that measures how entangled a system is with its environment. When a quantum system is perfectly isolated, its entropy is zero. All the information about it is contained within the system itself. But as it interacts with the environment, it becomes entangled. Information spreads out into the environment. The system state can no longer be described independently. You have to describe it together with its surroundings. This entanglement with the environment is what causes decoherence, the loss of quantum behavior in large objects. Your body is constantly interacting with air molecules, photons, thermal radiation. Every interaction entangles you a bit more with the environment, destroying quantum coherence, making you behave classically. In a sense, you're maximally entangled with the world around you, Information about your quantum state is spread into the environment so thoroughly that isolating you, seeing quantum interference from your body as a whole, would be impossible. This isn't a limitation, it's reality. It's the natural state of macroscopic objects, and there's something comforting about it. You're deeply connected to your environment, not separate, not isolated, thoroughly integrated with the space around you. Every breath you take entangles you more with the air. Every photon you absorb or emit entangles you more with the electromagnetic field. You're in constant quantum communication with the universe, trading particles, exchanging information, becoming ever more intertwined. And that deep interconnection, that thorough entanglement, is part of what makes you stable, what makes you real, what makes you you. The quantum world doesn't isolate, it connects. It weaves everything together into a seamless whole. Now, there's a fascinating quantum phenomenon called quantum Zeno effect that seems almost paradoxical. If you measure a quantum system repeatedly, you can actually prevent it from evolving. Normally, an unstable quantum state will decay over time, transitioning to a more stable state. But if you keep measuring whether it's decayed, each measurement resets it to the undecayed state if you find it hasn't decayed yet. The constant measurements freeze the system, preventing the decay that would naturally occur. It's named after Zeno's paradoxes about motion. Zeno argued that motion is impossible because to reach a destination, you must first reach the halfway point, then the halfway point of the remaining distance, and so on infinitely. Of course, motion is possible. Zeno's reasoning was flawed. But in the quantum realm, constant observation really can prevent transitions. This has been demonstrated experimentally. Quantum systems that would normally decay in some characteristic time can be made to last much longer if continuously observed. The act of observation, of measurement, interferes with the natural evolution. There's almost a meditative quality to this. By watching something constantly, you keep it in the present. It can't change, can't decay, can't move forward. Observation holds it in place. As you lie there, perhaps there's an analog in your own experience. If you keep checking whether you're asleep yet, you prevent sleep from coming. The constant observation, the continuous self-monitoring, interferes with the natural transition from waking to sleep. Let go of the observation. Stop checking. Allow the natural evolution to proceed. Trust that sleep will come without your having to watch for it. In both quantum mechanics and in your own experience, sometimes the best way to let something happen is to stop observing, to stop trying to control, to simply allow. Let's talk about something called Bell's inequality, which is one of the most profound results in quantum mechanics. John Bell proved mathematically that if quantum entanglement works the way quantum mechanics says it does, certain correlations between measurements should violate what's called Bell's inequality. If, on the other hand, there are hidden variables, secret information determining outcomes that we just don't know about, then the correlation should satisfy Bell's inequality. So, testing the inequality is a way to distinguish between quantum mechanics and hidden variable theories. The experiments have been done many times with increasing sophistication, and they consistently violate Bell's inequality, supporting quantum mechanics. This means the correlations between entangled particles are stronger than any hidden variable theory could produce. The universe really is non-local in a deep sense. Information about one particle's measurement really does instantaneously affect its entangled partner, no matter the distance. There's no hidden information determining the outcomes ahead of time. The randomness is genuine, and the correlation is real. This is sometimes called quantum non-locality, and it's one of the most verified and yet most counterintuitive aspects of quantum mechanics. Einstein called it spooky, and it is. But it's also real, tested, confirmed, beyond reasonable doubt. What does this mean? It means the universe is more interconnected than we ever imagined. What happens here can be instantaneously correlated with what happens there, across vast distances, in ways that seem to violate our intuitions about locality and separateness. You might feel isolated, separate, alone in your room, but at the quantum level, particles that were once together, that interacted and became entangled, remain connected. The universe maintains these threads of connection, these quantum correlations across time and space. You're not as separate as you feel. The particles in your body have histories of interaction with particles now scattered across the cosmos. Some trace of that entanglement remains, some quantum connection too subtle to observe directly but real nonetheless. In the quantum world, connection is deeper and more persistent than we ever imagined. And maybe that's something to carry with you as you drift towards sleep. You're connected, entangled, part of a vast quantum web that spans the universe. Let's think about quantum computing from a different angle. We mentioned it earlier, but there's more to say about what makes it remarkable. Classical computers work with definite states. A bit is 0 or 1, definitely, at every moment. Computations proceed by definite logical steps, each state leading deterministically to the next. Quantum computers work with superpositions. A qubit is 0 and 1 simultaneously in varying proportions. Computations proceed by manipulating these superpositions, allowing the quantum computer to explore multiple solution paths in parallel. But here's the subtle part. You can't just read out all the answers at the end. Measuring the qubits collapses them to definite states randomly. So how do you get useful information out? Quantum algorithms are cleverly designed so that wrong answers cancel out through quantum interference, and the right answer gets amplified. When you measure at the end, you're likely to get the right answer, not because you can see all the possibilities, but because the quantum evolution has been orchestrated to make the correct answer most probable. It's like conducting an orchestra. Individual instruments might play random notes, but when properly coordinated, they produce harmony. Quantum algorithms coordinate the quantum amplitudes so that everything adds up to something useful. This requires incredible precision. Small errors accumulate and destroy the interference patterns. This is why quantum computers are so difficult to build. They need to maintain quantum coherence, prevent decoherence, and execute operations with extreme accuracy. Current quantum computers are in what's called the NISQ era, noisy intermediate scale quantum. They have dozens to hundreds of qubits, but they're noisy, error-prone, limited in what they can do. Building larger, more reliable quantum computers requires solving immense engineering challenges, but progress is being made, and the potential applications are tantalizing. Simulating quantum chemistry to design new materials or drugs, optimizing complex logistics, breaking certain types of encryption, solving problems that would take classical computers longer than the age of the universe. As you lie there in the quiet, quantum computers around the world might be running their qubits in superpositions, exploring vast spaces of possibilities, searching for solutions in ways that leverage the fundamental strangeness of quantum mechanics. The quantum revolution isn't just about understanding nature. It's about using that understanding to build technologies that seemed like science fiction just decades ago. And we're at the very beginning of this revolution. Who knows what quantum technologies will exist in 50 years, in 100. But for now, for tonight, the quantum computers can keep computing. You don't need to think about them. Let them work while you rest, exploring their superpositions, their entanglements, their quantum algorithms, while you explore the simpler mystery of sleep. Now let's talk about something poetic. The hydrogen atom, the simplest atom in the universe, has a beautiful quantum structure. a single electron orbiting a single proton, nothing more. And yet, even this simple system has infinite complexity. The electron can be in infinitely many different states, each corresponding to a different energy level, a different orbital shape. The ground state, the lowest energy, has the electron in a spherical cloud around the nucleus. Excited states have more complex shapes, dumbbells, cloverleafs, intricate forms with nodes and lobes. Each state has a unique energy determined by quantum numbers. The principal quantum number describes the overall energy and size. The angular momentum quantum number describes the shape. The magnetic quantum number describes the orientation. These quantum numbers aren't arbitrary labels. They emerge from solving the Schrödinger equation for the hydrogen atom. They're imposed by the mathematics, by the wave nature of the electron, by the geometry of space itself. And every hydrogen atom in the universe has these same possible states, these same energy levels, these same quantum numbers. The hydrogen in your body, in the sun, in distant galaxies, all of it governed by identical quantum rules. There's something universal and eternal about these quantum states. They're not constructed or invented. They're discovered, revealed by the mathematics of quantum mechanics. They were true before life existed, before Earth formed, before the universe was 1 billion years old, and they'll remain true as long as hydrogen exists. You're made partly of hydrogen. Water molecules, H2O, contain hydrogen. Organic molecules, carbohydrates, proteins, fats, all contain hydrogen. And every hydrogen atom in your body has the same quantum structure, these same possible states. Most of them are in the ground state, the lowest energy configuration. But occasionally, a hydrogen atom gets excited, absorbing a photon, jumping to a higher energy state, and then it falls back, emitting a photon, returning to equilibrium. These quantum transitions happen constantly in your body, part of the chemical processes that keep you alive, and each one follows the same quantum rules that govern hydrogen everywhere in the universe. There's something deeply reassuring about that uniformity, that universality. The laws aren't changing, the quantum states aren't shifting. Everything is following reliable, consistent, eternal patterns. As you rest, you can trust in that consistency. The quantum world isn't chaotic or arbitrary. It's structured, rule-governed, dependable. The same rules that apply now applied yesterday and will apply tomorrow. The universe is coherent and self-consistent, even in its strangeness. And finally, let's think about the measurement problem one more time, from a more philosophical angle. We've talked about wave function collapse, but what does it really mean? Before measurement, the system is in a superposition. After measurement, it's in a definite state. Something changed, but what, and how, and why? Different interpretations give different answers. Copenhagen says the wave function isn't real, it's just our knowledge. And collapse is just us gaining information. Many Worlds says the wave function never collapses, the universe splits, and we find ourselves in one branch. Objective collapse theories say the wave function is real and really collapses, perhaps due to gravitational effects or other mechanisms we don't fully understand. Relational interpretations say states are defined relative to observers, not absolutely. Hundreds of pages have been written debating these interpretations. Brilliant physicists disagree about what quantum mechanics means, even though they all agree on what it predicts. The math works, the experiments confirm it, but the meaning remains elusive. Maybe that's okay. Maybe physical theories don't have to provide meaning, only predictions. Maybe the question, what's really happening, is a question physics can't answer or doesn't need to answer. Or maybe we're still waiting for a deeper theory, something that will make quantum mechanics seem obvious in retrospect, the way quantum mechanics makes atomic structure seem obvious. Either way, the mystery remains, and there's something beautiful about that. After a century of quantum mechanics, after all the successes and applications, the core mystery is still there, still puzzling, still inviting deeper thought. You don't need to solve it tonight. Nobody expects you to. The greatest minds of the 20th century pondered these questions and couldn't agree, so you can let it rest. The mystery can wait. It's been waiting this long. It can wait another night. Let the questions fade. Let the interpretations blur together. Let the measurement problem dissolve into the general haze of approaching sleep. Some mysteries are meant to be pondered, not solved. Some questions are worth asking without expecting answers. And that's quantum mechanics, a theory of incredible precision and utility, built on a foundation of profound mystery. We can calculate anything we need to know, and yet what it all means remains beautifully, frustratingly unclear. Perhaps that's the final lesson of quantum physics. Knowledge and understanding are not the same thing. We can know what happens without understanding why. We can predict outcomes without grasping causes. We can use tools without fully comprehending them. And that's enough. It has to be. Because the universe doesn't owe us comprehension. It only offers patterns, regularities, predictions. And those, remarkably, are sufficient to build civilizations, to create technologies, to explore the cosmos, to wonder and dream. So rest now, quantum traveler. You've learned enough for one night. Let the strangeness settle into the background. Let the certainty of sleep override the uncertainty of quantum superposition. Let yourself collapse from the many states of wakefulness into the single state of rest. The quantum world will be here tomorrow, as strange and beautiful as ever. For now, for tonight, let it be. Let yourself be. Let sleep come, gently and naturally, as inevitable and mysterious as the collapse of a wave function. Good night. Now, all of this quantum strangeness has led to technologies that are reshaping our world. We've already mentioned quantum computers briefly, but they're worth exploring a bit more because they represent such a radical departure from ordinary computing. Classical computers process information as bits, ones and zeros. Everything reduces to these binary choices, and computation happens by manipulating these bits according to logical rules. It's very efficient, and classical computers have become remarkably powerful. But quantum computers do something fundamentally different. They use qubits, quantum bits. They can be in superpositions of 0 and 1 simultaneously. A qubit isn't just 0 or 1, it's both, until you measure it. This sounds like a small difference, but it has enormous implications. Two classical bits can be in one of four states, 0, 0, 0, 1, 10, or 11. But two qubits can be in a superposition of all four states at once. 3 qubits can represent all 8 possible 3-bit patterns simultaneously. The possibilities grow exponentially. A quantum computer with just a few hundred qubits could, in principle, explore more states than there are atoms in the observable universe. It's a form of parallelism that classical computers simply can't match. But there's a catch. Several, actually. Qubits are incredibly fragile. They require near absolute zero temperatures, extreme isolation from the environment, because any tiny disturbance causes decoherence, collapsing the superpositions and destroying the quantum computation. And you can't just read out all the possible answers. When you measure a qubit, it collapses to 0 or 1 randomly. The art of quantum computing is designing algorithms that amplify the correct answers and cancel out the wrong ones. So when you finally measure, you're likely to get the solution you're looking for. Despite these challenges, quantum computers are being built. They're still in early stages, noisy and error-prone, but they're working. They've already performed certain calculations that would be impractical for classical computers. In the future, quantum computers might revolutionize drug discovery by simulating complex molecules, crack current encryption methods, or optimize complicated systems in ways we can barely imagine. Or they might remain specialized tools, useful for certain narrow tasks but not everyday computing. Either way, they represent something profound. We're learning to harness the strangeness of quantum mechanics, to use superposition and entanglement not just to understand nature, but to build new technologies. We're taking the most counterintuitive aspects of reality and making them work for us. As you lie there, perhaps using a device that already relies on quantum mechanics and its transistors and LEDs, you're connected to this quantum technological revolution. The future is being built on principles that, a century ago, seemed like pure abstraction, philosophical puzzles with no practical use. And that's often how science works. Today's mystery becomes tomorrow's tool. Today's impossible becomes tomorrow's mundane. But let's return to something more intimate. Your body, your cells, the very processes of life. Are they quantum? For a long time, biologists assumed quantum effects didn't matter in living systems. Biology is warm, wet, noisy. Quantum effects are fragile, requiring cold, isolation, careful control. Surely life operates purely according to classical physics, but evidence is mounting that quantum mechanics plays crucial roles in biology. One of the most compelling examples is photosynthesis, the process plants use to capture sunlight and convert it to chemical energy. When light hits a chlorophyll molecule, it excites an electron. That energy needs to travel through a complex network of molecules to reach a reaction center where it can be stored. Classical physics would suggest the energy hops randomly from molecule to molecule, losing a lot of efficiency along the way. But experiments suggest something stranger is happening. The energy seems to explore multiple paths simultaneously, as if it's in a quantum superposition, sampling different routes through the molecular network. This allows it to find the most efficient path, delivering energy to the reaction center with remarkable speed and efficiency. The fact that quantum coherence can survive long enough in a warm, chaotic biological environment to affect the outcome is surprising and beautiful. It suggests that evolution has found ways to exploit quantum mechanics, to use these subtle effects to improve efficiency. Another example is bird navigation. Many birds can sense Earth's magnetic field and use it for navigation during migration. How do they do this? One hypothesis involves quantum entanglement. In the bird's eye, there may be molecules that, when struck by light, create pairs of entangled electrons. These entangled electrons are sensitive to magnetic fields in a way that depends on quantum mechanics. The bird's brain might be reading out quantum information to determine which direction is north. This is still being investigated, but if true, it means birds are, in a very literal sense, quantum sensors, using entanglement to navigate across thousands of miles. Even your sense of smell might involve quantum mechanics. The traditional theory says smell receptors recognize molecules by their shape, like a lock and key. But some researchers propose that receptors might also be sensitive to molecular vibrations, using quantum tunneling to detect the vibrational frequencies of odorant molecules. This would explain why some molecules with different shapes can smell similar, or why molecules with similar shapes can smell different. They're being recognized not just by shape, but by quantum vibration. These ideas are still somewhat controversial, but they point to a fascinating possibility. Life might not just be subject to quantum mechanics, like everything else. Life might actively use quantum effects, evolved over billions of years to exploit these subtle phenomena in ways we're only beginning to understand. You are, in this sense, a quantum being. Your cells, your molecules, the very processes keeping you alive, may depend on quantum mechanics in ways both fundamental and surprising. You're not just made of quantum particles. You might be using quantum effects to see, to smell, to exist, and that's extraordinary. The line between quantum and classical, between the strange microscopic world and the familiar macroscopic world, is blurrier than we thought. Quantum mechanics isn't just about particles and accelerators or atoms in laboratories. It's about you, here, now, alive and conscious. Let's drift now toward our conclusion, but there's one more aspect of quantum physics worth contemplating as you settle into sleep. It's the question of randomness, of whether the universe is fundamentally deterministic or genuinely unpredictable. In classical physics, randomness is ignorance. If you flip a coin, it seems random because you don't know exactly how you flipped it, the air currents, the surface it lands on. But in principle, if you knew all those details, you could predict the outcome perfectly. The randomness is apparent, not real. Quantum mechanics suggests something different. When you measure a quantum system, the outcome is genuinely random, not because you don't know enough, but because there's no fact of the matter beforehand. The electron's spin isn't secretly up or down before you measure it. It becomes up or down when you measure it. And which one is truly random? This bothered Einstein deeply. He believed in an underlying determinism, a universe where everything has a cause, where randomness is just hidden order. His famous quote, "God does not play dice," expresses this conviction. But experiments have consistently supported quantum mechanics. The randomness seems real. The universe, at its foundation, has genuine unpredictability built in. What does that mean? Philosophically, it's profound. It means the future isn't completely determined by the past. At every moment, the quantum randomness at the microscopic level creates true novelty. The universe is, in a sense, creative, generating outcomes that weren't predetermined. Some find this unsettling. A universe with randomness feels less orderly, less comprehensible, but others find it liberating. It means reality isn't locked into one predetermined path. Possibility is real. The future is open. And yet, this randomness isn't chaos. Quantum mechanics makes incredibly precise statistical predictions. The randomness follows patterns, obeys rules. It's structured randomness, if that makes sense. Rolling dice is random, but over many rolls, you'll get each number about 1/6 of the time. Quantum measurements are similar. Individual outcomes are unpredictable, but the probabilities are exact. The randomness has a shape, a distribution, a mathematical form. Perhaps this is the deepest lesson of quantum mechanics. The universe is neither purely deterministic nor purely chaotic. It's something in between, something richer. It's probabilistic, filled with genuine randomness that nonetheless follows precise rules. As you drift between waking and sleep, your mind does something similar, doesn't it? Your thoughts arise somewhat randomly. You can't completely control what you'll think next, and yet there are patterns, associations, tendencies. It's not complete chaos, it's structured spontaneity. Maybe consciousness and quantum mechanics share something deep, or maybe it's just a metaphor. Either way, both point to a universe that's more subtle, more nuanced than simple either-or categories can capture. We've journeyed far tonight, from the first hints of quantization in Planck's equations, through Einstein's photons and the wave-particle duality, through the strangeness of superposition and entanglement, through tunneling and the quantum vacuum, through measurement and uncertainty, through the applications in technology and hints in biology. We've seen that reality at its smallest scales is nothing like the solid, predictable world of everyday experience. It's fuzzy, probabilistic, interconnected in non-local ways, filled with possibility and becoming rather than fixed being. And yet, from this quantum foundation, the classical world emerges. Atoms settle into stable configurations. Molecules form. Chemistry happens. Life arises. Consciousness appears. Somehow, from the quantum haze, the familiar world of objects and events crystallizes. How that happens, how we get from quantum to classical, from possibility to actuality, remains one of the deepest questions in science. Decoherence explains part of it. Interactions with the environment collapse superposition so quickly that large objects never exhibit quantum behavior. But the full story, the complete picture of how the two realms connect, is still being worked out. Perhaps that's appropriate. Perhaps it's fitting that the boundary between quantum and classical remains mysterious, because it's the boundary between two ways of being, two types of reality. It's not a sharp line, but a gradual transition, a region where one kind of physics fades into another. You exist in that transition zone, in a way. You're made of quantum particles, but you're large enough to behave classically most of the time. You're at the edge, the meeting place of two worlds, and that's a special place to be. As you finally release your hold on wakefulness, let yourself appreciate the journey you've taken tonight. You've explored ideas that challenge the greatest minds of the 20th century. You've glimpsed a reality stranger and more beautiful than our ancestors could have imagined. And tomorrow, when you wake, the quantum world will still be there, underneath everything, in the light streaming through your window, in the atoms of your breakfast, in the electrons flowing through your devices, invisible but essential, strange but real, forming the foundation of all that exists. Quantum mechanics isn't just a theory about particles. It's a reminder that reality is deeper than it appears, that certainty is not the same as truth, that mystery and precision can coexist, that the universe is still capable of surprising us. And maybe that's a comforting thought as you drift off. The world is more than it seems. There are depths beneath depths, wonders within wonders. Not everything is known. Not everything is knowable. And that's okay. Let your breathing slow. Let your muscles relax. Let the quantum world fade into the background as your classical experience of rest takes over. The probabilities of your neural firing patterns are shifting, adjusting, guiding you gently towards sleep. You've learned tonight that observation collapses possibility into actuality. So stop observing, stop thinking, let the wave function of your consciousness spread out, diffuse, explore the space of dreams where normal rules don't apply and anything seems possible. From quantum uncertainty to the certainty of sleep, from the strangeness of superposition to the simplicity of rest, from the vast interconnected web of entangled particles to the intimate privacy of your own dreams. Thank you for joining me on this journey through the quantum realm. Thank you for your curiosity, your patience, your willingness to sit with ideas that don't always make immediate sense. Whether you're still awake, clinging to the last threads of awareness, or whether you've already slipped away into sleep, I hope you carry something of this with you, a sense of wonder, an appreciation for mystery, a comfort in uncertainty. The quantum world teaches us that not knowing isn't failure. It's honest, it's realistic, it's humble. The universe is under no obligation to make sense to us, and yet it offers us these glimpses, these mathematical patterns, these experimental confirmations, invitations to understand just a little bit more. Sleep well, quantum traveler. Rest in the knowledge that you're part of something vast and strange and beautiful. The same forces that govern atoms govern you. The same fields that fill the cosmos fill your body. You're made of stardust and quantum foam, probability and certainty, wave and particle. And right now, more than anything, you're tired. So let go. Let the quantum mysteries fade. Let tomorrow worry about understanding. Tonight is for rest, for release, for the sweet uncertainty of sleep. From all of us here at Sleep Knowledge, thank you. May your dreams be peaceful, your sleep deep, and when you wake, may the world seem just a little bit more magical, knowing what lies beneath its surface. Good night.